All right. So, yes. Oh, thanks. 7.4 notes. Our goal is to simplify radicals and use a calculator to approximate values. Now, you've heard me say this word radical before. All it is it's a square root sign. But it's a more generic term than just saying a square root, because it can be a cubic root or a fourth root or a fifth root, etc., based on this number right here. This number here is what we call the index. This symbol here is the actual radical sign. And this number here is called the radicand. So what are square roots? Something that you probably already know is what the square root of 16 is. What is the square root of 16? 4. And you guys already knew the answer. Now the reason why your answer is 4 is because in a square root you have an invisible 2 right here. Your index is an invisible 2. Okay? So what that means, where this comes from, is that 4 squared is equal to 16. That's why the square root of 16 is 4. It says, what do I square? And I get 16. You square 4. Okay, so when you're taking a square root, what number do you square to get 16? 4. You could also represent this by taking 16 to the power of 1 over 2. If it is the sign that's on the radical sign, so the index, that's actually the denominator if you want to write it as an exponent. Okay? And this is much easier to type in your, well, I shouldn't say it's easier. With a square root, it's the same. But on your calculator, you have a square root symbol. Okay, so you could do the square root of 16. It tells you it's 4. If you take 16 to the power of, in parentheses, put 1/2. And watch what happens. I want you to type in your calculator right now 16 to the power of 1/2, because I want to make sure you know how to accurately type it in. The 1/2 would have to go into parentheses. Okay, let's make sure we're getting 4. Does anyone need help with that? Okay, so then let's talk about another example. If I wanted to talk about the cubic root of 8. Now, we've talked about cubic roots before, not specifically, but I have asked you, what number do you cube and get 8? 2. And so that's exactly what we're asking right here. What number do you cube, because that's the index, to get 8? It's 2. We know this because 2 to the third power is 8. Okay. Now, how could I also write this? I forgot to finish filling out that one. That equals 4. If I wanted to instead write 8 to an exponent, a cubic root is what exponent? What would it be? 1/3. Very good. So again, the denominator is just the index. The numerator is the exponent that is on our original number. And in these cases, your exponent isn't shown, so we know it has an exponent of 1. Are you with me? So it's 1 over 3 would be the exponent. Okay, type in your calculator. What is 8 to the 1/3 power? What is 8 to the power of 1/3? 2. Try this next one. Try 243 to the power of 1/5. What is that in your calculator? 3? Anyone else get 3? You should get 3. Okay, what is the radical for 243 to the power of 1/5? How would I write that as a radical with a radical sign? Go ahead. It's the 5th root, so we have a 5 on the outside of the radical, 5 is the index, 5th root of 243. Okay. This comes from the fact that 3 to the power of 5 is equal to 243. So I just wanted to go through on what these symbols will look like and how to evaluate them and make sure we know how to type them into a calculator. Now there is a way that you could also type it in this form in your calculator, but it looks funny. The caret is how we do an exponent, but if you hit like a 5 and then second that caret, it looks like 5 times this radical with an x root, but the 5 is actually in place of that. So 5th root of 243 will also give us the answer of 3. So you can type it in that way. I don't usually prefer to type it in that way, just because I like to be able to see the actual exponent versus I don't see a 5th root there. It looks to me like it's saying 5 times that radical. So it gets a little bit confusing on what the calculator shows versus the operation you're actually doing. Does that make sense? So as long as you know how to evaluate in a calculator, I don't really care. You can do it either way you want. All right, so simplifying roots. You guys already know how to do the first one, okay? Our big idea here is that you can't square root it unless something's being squared. So the square root of is 121 something squared. It is. It's 11 squared. So we can write this as 11 squared. Can we write something squared and get x to the 4th? X squared. X squared squared, remember powers to powers multiply, so x squared squared is x to the 4th. Okay, now how about the y? Can we write y as something squared? Y to what power? If it was to the 4th power, 4 squared, or y to the 4th squared would be y to the 8th. So it has to be a 3 because 3 times 2 gets us 6. A power to a power multiplies. Are we okay with that? Okay. So if you square root 11 squared, what do you get? Well, if you square 11, you get 121. But if you square root it, what do you get? 11, right? Because if you square root something that's being squared, doesn't it undo it? Isn't squaring something and square rooting something just undoing each other? Aren't those like inverse operations? They're undoing each other. So if you're square rooting 11 squared, you're left with 11. If you square root this squared, you're left with x squared. If you square root this that's being squared, you're left with the y to the 3rd. Do you see how that works? Okay, I'm going to show you another way you could write this. instead of writing it as a square root, how else could you write it? Something that might look more familiar to you. A square root is what exponent? 1/2. Okay, so you could take this and write it like this. This is your other option to show your work here. What's 121 take to the 1/2 power? It ends up being 11. X to the 4th raised to the 1/2, you're going to multiply powers to powers, right? So what is 4 times 1 divided by 2? For the y, what is 6 times 1 divided by 2? And notice you'll get the exact same answer either way. Okay. Yes? No, I don't care. I don't care how you do these, as long as you can get to them. But what's your index here? What's your invisible index? The 2. A square root is a 2. Look what happens in your exponents from the beginning to your last step. Other than the 121, because you can't see an exponent on it. What's happening to those exponents? They're divided by the index. They're divided by 2. Okay. The reason why are they divided by 2 was because we're actually multiplying them by 1/2 if you're taking a power to a power. I don't care how you think about this as long as you can get to that to be your final answer. Does that make sense? Okay. Other people like to expand it out. So let me do a third color here. You could write it from the beginning as 11 times 11 times 1, 2, 3, 4 x's and 1, 2, 3, 4, 5, 6 y's. You can't even see that. There we go. Okay. And because the index is a 2, these have to pair before they can come out. These pair, these pair, these pair, these pair, and these pair. So how many pairs of 11 do you have? Now you have 1 pair, right? 2 makes a pair, but you only have 1 pair. So your answer here would be 11. How many pairs of x's do we have? So we have x squared. How many pairs of the y do we have? Y to the 3rd. Now we had to pair them because of the index being 2. That's another way you can think about this problem. I don't care which way makes sense to you. Pick one that makes sense to you and go with it. My piece of advice is pick one way and stick with it. I usually go this route and just divide by the 2. Divide by the index. That's the way I go about it. Okay? Let's look at this next one. -8. What do you multiply by itself 3 times and get -8? 2 times 2 times 2 would be a +8. -2 times -2 times -2 is -8. So our answer here, starting with the -2, okay, how about the x to the 6th? X squared. Once you have the number done, it's easy from there because you just take that exponent and divide by the index. 6 divided by 3 is going to give me 2. What's the exponent going to be on my y? 3. And that's your final answer. I know I showed a lot of work for the first one because I wanted you guys to see where it was coming from. But there's not much work to actually show on these problems. Are we okay with that one? All right, let's try the next one. There was a negative sign out front, so you want to leave that negative sign out front. This one is grouped already. So your answer is going to be grouped. You're not changing anything there, but you're going to use that exponent that is to the 8, and what does it become? 2. Because it was 8, we divide by 4, we get 2. And that's as far as you go with that one. Do we have questions so far? Yes.
So, number 2. You don't divide by 1/2.
Well, technically you're multiplying your exponents by 1/3 because this is negative 8 x to the 6th y to the 9th to the 1/3 power because your index there is 3. Does that make sense? So if you were taking x to the 6th to the power of 1/3, 6 times 1/3 is the same as 6 times 1 is 6. 6 divided by 3 is 2. 9 times 1 is 9. Divide by 3 is 3. Does that make sense? So it has to depend on what that index is. Okay. You can put negative 8 to the power of 1/3 in your calculator. It will tell you it's negative 2. Now, we run into an issue if this was not a perfect cubic number. Okay, that's when we would run into an issue. All right, let's try number 4. Now, number 4 is a little bit tricky because what's our index here? And if you take the square root of 72, what's your answer? A decimal. So we can't do that. So what we need to do then is go to our list of perfect squares. So, because that index is a 2, we need a list. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, dot, dot, dot. Okay? What are these perfect square numbers? We have 1, we have 4, we have 9, 16, 25, 36. Right? We know how to come up with that list. Now, the reason we wanted to come up with that list is because we can take a square root of those numbers. So, can we write 72 as one of these numbers times something else?
6 times 2.
What is it? 36 times 2, yes. So we can write the square root of 36 times 2. Here's another issue. Does 5 divide by 2? No, not nicely. So what we want to do is we want to write this in 2 separate things. So we're going to write it as x to the 4th times x. That's still x to the 5th, correct? And I wrote it like that because x to the 4th can be divided by 2. Do you see that? Okay, so then what about, oh wait, y to the 8th, that is divisible by 2, so I'm okay with that one. Are we, so I can leave y to the 8th. Are we okay with that so far? Okay, so anything you can take the square root of is going to come out front. So what's the square root of 36? So the 6 will be out front. What's the square root of 2? You can't do it. 2 has to stay on the inside. What's the square root of x to the 4th? X to the 2nd, so that comes out. What's the square root of x? Can't do it. It stays in. What's the square root of y to the 8th? Y to the 4th. So that comes out. And that problem's done. Yes, go ahead.
So, for the, like, how did you get the 6? And the 2?
Because the square root of 36? The answer is 6.
Oh, and then the 2.
Because 36 times 2 is equivalent to 72.
Oh, okay.
So 36 times 2 is equal to 72. I needed to write 72 because if I tried to do the square root of 72, it's a decimal. So I can't take the square root of that number. So instead I had to use one of my perfect squares. That's why I came up with my list of perfect squares to say what could I have here in place of 72. So you have to write it as a multiplication problem. Now, 5 is not divisible by 2, so I wrote it as 4 and 1, right? X to the 4th times x is x to the 5th. Because when you multiply powers with, or exponents with the same base, you add up the exponents. So 4 and 1 is 5. Does that make sense? Okay. There are other questions on this one? All right. So, number 5. Can you take a cubic root of 16? Okay. We could try it. I could do 16 to the power of 1/3, and it doesn't work. So far, so good? So instead, I want to write that as something to a third power, so times something else. So I need a list of perfect cubic numbers. So 1 cubed, 2 cubed, 3 cubed, 4 cubed. I'm going to need this list. So what's 1 cubed? 1. What's 2 cubed? What's 3 cubed? What's 4 cubed? Okay, and that's plenty high enough because I'm only talking about the number 16. So how could we write 16 using one of these numbers? 8 times 2. So I'm going to change the way this is written. I'm going to change this to 8 times 2. Is 10 going to be divisible by 3? No. So how should I write this then? X to what power would be divisible by 3? To the 9th. X to the 9th times what gives you x to the 10th? X to the 1st, yeah. So that'll give you x to the 10th. Is 4 divisible by 3? No. So we have to write it as what? Z to the 3rd times z. Okay, now we can take and you can even like underline or do something to this. I can take the cubic root of this. I can take a cubic root of this. I can take the cubic root of. The rest of it's going to stay inside. So I'm going to have a 2 left on the inside, an x on the inside, and a z on the inside. What is the cubic root of 8? The cubic root of 8 was 2. 2 cubed was 8. Okay, so I left the 2 on the inside. X to the 9th, the cube root it. What do you get? X to the 3rd power. X I couldn't do anything with. I left it on the inside. Z to the 3rd, take the cube root. What do we get? Z to the 1st. I don't care if you write to the 1st or don't write it, doesn't matter. And you have the Z on the inside still. Give me like a 1 to 5. I'm following you. I feel like I got this. Down to a 1. I don't know where I'm at, but I'm definitely not in Algebra 2. Okay. So, this next one is a 4th power, or a 4th root. Yes?
So, I'm just a little confused because I don't know but so x to the 9, you just do 9 squared.
9 divided by 3 is x to the 3rd. Because what you're doing is you're taking x to the 9th to the 1/3 power. So if you wanted to write this out instead, you could write 8 times 2 times x to the 9th times x times z to the 3rd times z to the power of 1/3. Because if you're taking a cubic root, it's the same thing as taking something to the 1/3 power. Powers to power, so you can put in your calculator 8 to the power of 1/3, and it gives you 2, so it's going to go to the outside. If you try 2 to the power of 1/3, it's going to give you a decimal, so we can't evaluate that, so we're going to leave 2 on the inside. X to the power of 9 raised to the power of 1/3. A power to a power multiplies. So 9 times 1 is 9. Divide by 3 is 3. So we write x to the 3rd on the outside. Now this one, I'm not going to write it as x to the 1/3 power. It's the same thing because it's in that cubic root. Z to the third raised to the 1/3 becomes just Z, and Z to the 1/3 remains in that cubic root. Did that answer your question?
I think so.
Okay. All right, so looking at number 6 then, we're trying to take a fourth root. So we have to see if 32 can be taken, if you can take the fourth root of 32. If not, we'll need our list of perfect quartic numbers. Okay, so can you take the fourth root of 32? No. So, okay, so 1 to the 4th power, 2 to the 4th power, 3 to the 4th. We have to figure out what these perfect numbers are raised to the 4th power. So 1 to the 4th is going to be 1. What's 2 to the 4th? What's 3 to the 4th? I don't even have to go any further because I know that I would already have it in my list if it's possible. Do any of these numbers go into 32? 16. So I'm going to leave the 3 on the outside times the 4th root of 16 times what gets you 32? 2. X to the, am I going to be able to divide 10 by 4? No, so what number will I have to use here? X to the 8th, because 8's divisible by 4. But x to the 8th times what will give me x to the 10th? X squared. Okay. Is y to the 3rd divisible by 4, or 3 divisible by 4? No. Is there a smaller number than y to the 3rd that you could use? What is it? Well, is 2 divisible by 4? No. Nothing. Right? So I'm going to have to leave that y to the 3rd, and I'm just not going to be able to pull anything out there. I would need 4 y's to group together to go outside. Okay? If you think about it, how we did this one. Okay, so we have the 3 on the outside still. We have a 4th root. What is the 4th root of 16? What do you take to the 4th power and get 16? 2. So 2 is going to go on the outside. You can't take the 4th root of 2, so 2 stays on the inside. What's the 4th root of x to the 8th? X squared, because 8 divided by 4 is 2. So x squared will go on the outside. Can you take a 4th root of x squared? No, 2 is not divisible by 4. So x squared stays on the inside. Can you do anything with y to the 3rd? No, because 3 is not divisible by 4. So y to the 3rd stays on the inside. So wait a minute. The only extra thing we can do here is we have 3 times 2 now on the outside. Well, what's 3 times 2? So we can change the outside to read 6x squared times the 4th root of 2x squared y to the 3rd. Are we okay with that? Okay, so that's the gist of our examples. All right, let's flip to the back side. And there's one additional thing we need to talk about. And it's to simplify using absolute values. And once we get the idea of this, we'll go back and put absolute value bars in where necessary. So just to get you an idea of where this comes from, if I take negative 6 to the 4th power and I take 6 to the 4th power, what's the answer that I get right here? Negative 6 times negative 6 times negative 6 times negative 6. 1296? What answer do I get over here? Same thing. Okay. If we take any number to an even power, your answer is always positive. This is because two negatives multiplied together make a positive. So if you have something to the fourth power, you have negative 6 times negative 6 is a positive 36. Multiplied by an odd number, it would turn back negative. An even number, it turns back positive. Do you see how that would make sense, right? If we multiply a bunch of negative 6's together, every odd number that you multiply will turn it back to negative. Every even number you multiply by will turn it back to positive. Does that make sense, what I'm saying? Okay, so whenever we take anything to an even power, whether it's a negative to begin with or a positive to begin with, our answer always is going to be positive. Okay. Now, if it was taken to an odd power, like 3, that's when a negative sign can show up. Because negative 6 to the third power would actually be a negative number. Negative 6 times negative 6 is 36, times negative 6 is, I don't know, 216. So negative 216 would be your answer. Okay? Does that make sense? So if it's taken to an odd power, your positive and negative, it could be either one, depending on what you start with. But if it's raised to an even power, it's always going to be positive. Okay, so if we have the fourth root of x plus 2 raised to the fourth power, is your answer going to be positive or negative? X plus 2, since 4 divided by 4 is 1. It has to be positive. So your answer there is no. It's not going to be the positive or negative. No, because it was raised to an even power. Since it was originally raised to, since it was originally raised to 4, we knew it had to be a positive. So when we take the fourth root of it, it still has to be a positive. So what we do here instead is we use absolute value brackets to show that that has to be a positive answer. Okay? So you use this when you went from an even power to an odd power, because you were at 4 and then you went to 1. You kind of see that? So we'll do 2 examples here and actually simplify them and show you the difference. Okay? So this first one here, the fourth root of 16 times this grouped value. Okay? What's the fourth root of 16? Can you do it? The fourth root of 16. Can you do it? What is it? 2? Okay. So the fourth root of 16 is 2. Can you take the fourth root of something to the 12th power? Okay, what is the new power? 12 divided by 4 is 3. Okay. So, here's the thing. We were at an even power, so that had to be positive. Is your answer still going to show up positive? Not necessarily. So in that case, around just that thing, we need absolute value bars to show that it will remain positive. So we'll put a little arrow here, and we'll write it in. Was raised to an even power. So it went from even to odd. Okay, so when it goes from even to odd, you need those absolute value brackets. Let's try this one over here. Can you take the fourth root of 16? It's still going to be 2. Can you take the fourth root of something raised to the 16th power? What is the new power? To the fourth power. Okay? This would automatically show up even. You see that? Because it's raised to the 16th power. This is still going to show up even, because it's even, it will show up positive. because this is even, this will also show up positive. It's not necessary to have absolute value bars because it's already raised to an even power. It's going to be positive. Do you see the difference? So this one was even to even, which only shows positives. And then the absolute values are not necessary. So absolute value bars are not necessary there. So now that we have this idea of these absolute value bars, we're going to flip the page back and do those examples that we did, and we're going to find any that need absolute value bars. Am I good to flip this? Okay, so looking at number 1, did we have anything that went from even to odd? The y did. The y was to the 6th, and now it's to the 3rd. So what we need to do is we need to put absolute value brackets around just the y to the 3rd. In number 2, did we have anything that wasn't even and now is an odd? Nope. We had an even to an even, so we're good. And we don't have to worry about if it started as an odd. So far, so good? All right, let's look at number 3. Did we have anything that went from an even to an odd? Nope. We're good. Now the bottom 3, 4, 5, and 6, you do not even have to look at, because if there's ever stuff left on the inside, you don't have to worry about absolute values. So if you have stuff on the outside and inside, don't worry about absolute values. So when your answer has stuff on the outside and on the inside, outside and on the inside, outside and on the inside, we don't have to worry about absolute values. Our problems are done. Coolio? So you guys still have quite a bit of time to get started on this assignment. The assignment is your Friday work. Okay? So if you look, 1 through 21 are all just simplifying. It does say to use absolute value symbols when necessary. Okay? So I would do them all first and then go back and check every single one for the absolute value bars, because a lot of times it's a step that's forgotten about. So if you do it all at once, then you're kind of golden. And next week when you have your quiz, that'll probably be a reminder that's on the board, is to don't forget about absolute value bars, just like I usually put up those reminders. Okay? On the back side for 22 through 29, it asks you to evaluate in a calculator. Okay? So you can choose, you just have to know how to use a calculator and evaluate these numbers here. Okay, so you guys have the rest of the time to work.